All right, to understand equivalent sine and cosine functions, we first need to have a good understanding of the sine and cosine function themselves, and specifically the pattern as you go around in increments of 90 degrees or pi over 2 radians. So if you look at the sine function here, it starts at 0, right? This is where we start. And then if you go to sine of pi over 2, that is 1. And to see that or understand that, we can look at the graph. We have both sine and cosine here. We can see that it does start at 0, and then it goes up to 1, and then back down. But the reason for that is important to understand, and that's because sine is just the y value. And I have this simulation here from University of Colorado that they made, and I think it kind of illustrates that here. If you look in the center, you can see the green arrow that represents the y value on a unit circle. So since sine is the opposite or y value over the hypotenuse, which in this case is just 1, then sine of theta is just the y value. So it starts at 0, and then it goes up to 1, and then it goes down to 0 again. And then when you go from pi to pi over 2, it's negative. So it goes down to -1 and then back to 0 again. And you can see that here on a graph at the bottom. As you move around, you can see it just the value of it changing, and that's why the graph looks that way. So this is kind of the sketch that I make, and it just shows, again, in increments of pi over 2, that it starts at 0, it goes up to 1, and then it goes back to 0, and now because sine is the y value, it's -1, and then on and on and on it goes. Cosine, on the other hand, starts at 1, and you can see that on the graph here, but you can also see that on this simulation. If I change it to cosine, you can see that cosine is the adjacent side, or the x value, over the hypotenuse, which again is always just 1. So the cosine is just the x value on a unit circle as you start at 0 radians or degrees and go around. So when you start here, it's 1, and then it goes to 0, and then it goes to -1. And if you keep going from here, you'll see that it goes down to 0. But also, if you start here, which I could have left it as 3 pi over 2 radians, or in this case, I'm kind of making it -pi over 2 radians. But if you do that, you'll see that it goes smoothly from 1 and then back to 0. And that's what that looks like. So on this sketch here, I can say, well, cosine, which again is just the x value, it starts here at 1. And then as you go around, it's the x value is now 0. And then here the x value is -1, back to 0, and on and on and on it goes. So the only real difference here is that the sine function starts at 0 and then goes to 1 and then back to 0, whereas the cosine function starts at 1 and then goes to 0 and -1. But understanding that, we can make equivalent functions or expressions. So if I have something like this, which is sine of theta plus pi over 2. So the way I do this is I just say whatever the value is here with theta in this argument, that's my starting point. So I'm going to start at pi over 2, and I know that at pi over 2, the y value is 1. And then I'm just going to go from there. So in starting here, I then go around the way I normally would, and then the y value here is 0, and here it's -1, and then it goes back to 0, and on it goes. So I need an expression, sine or cos, and I think in this case, because it's starting at 1, that means I'm looking back here at this cosine function. So I can just say, well, this is equal then to cos of theta, because it starts at 1 and then goes to 0 and then to -1. If I have a cosine function, again, I take this as my starting value. So I start at -pi/2 radians, and I know at that point the x value is just 0. So that's my starting value. And then as I go around, cosine here is 1. And then the x value here is back to 0. And then here it's -1, and on it goes. So I really only need the first couple numbers, right? I have to start at 0 and then go to 1 and then back to 0. That's a sine function, right? So that's just sine of theta. Now, they're not always just sine or cos. In this one here, right, I'm going to start at 3 pi/2, and the sine, which is again is the y value of 3 pi/2, is -1. But also here I'm going to go in the negative theta direction. So this means I have to go in the negative direction instead of the positive. So that means I actually have to go this way. And again, in going by increments of pi/2, because that's really the only pattern I need to do this, the y value here would be 0, and then it would go up to +1, and here it would go back to 0, and then it would go back to -1. So because it's starting at 1, well, it's -1, but because of the 1, I'll make it a cosine function. But because it's starting at -1 instead of positive, I'll just put a negative sign in front of it. For a cosine of pi minus theta, so again, my starting value is just whatever is in this bracket with the theta, which in this case is pi, so that's my starting value. So if I start at pi, the cosine of pi is -1, because the x value at pi is -1. And then once again, like the last one, I'm going in the negative direction. So that means I'm going to go here to 0 and then to +1, back to 0, and on. So I need a function that starts at 1. That again is cosine, but because it starts at -1, I'll just make this negative cosine of theta. There's some more practice ones here, but definitely give these a try on your own, and then look at me do them if you want. But it's the same thing that I'm doing here. I'm just going to take whatever the starting value is, and it doesn't matter if this value comes first or second. I'm going to start at pi, and sine is the y value. So here it's 0, and then I'm going to go in the positive direction because this is a positive theta. So that means I'm going to go from 0 to -1, back to 0, and on I go. So a function that starts at 0 is sine, but because it's going to -1 instead of positive, I'm just going to make that negative sine theta. For this one, I'm going to start at pi/2, and the cosine here is 0. And then I'm going to go in the negative direction. So I'm going to go from 0 to 1, because cos again is the x value, and then back to 0, and on I go. So that's basically the pattern of a sine function. It starts at 0, goes to 1, and then back to 0. This one here, sine, so I'll start at pi, and the sine of pi is 0. And then from there, I'll go in the negative direction, so I will go to 1, and then back down to 0. And that is the exact same pattern as a regular sine function. So that's just sine theta. At pi, cosine, I think we've done this a few times now, is -1. And then if I go in the negative direction, cosine here is 0. And then it's back to 1. So again, this is just a negative cosine function. At pi over 2, a sine is 1. And I'm going in the negative direction. So that means here the y value is 0. And then here it's -1. So this is a cosine function. And finally, I'm going to start at -3 pi over 2. So that's up at the top, and it's a cosine, so it starts here at 0. Again, that's going -3 pi over 2, which is the same as going positive pi over 2. And I'm going to go in the negative direction. So I start at 0, and then 1, and then back to 0, and on I go. And this is a sine function. Okay, tan, on the other hand, the period of a tangent function is pi, not 2 pi. So that's how it's different from a sine and cosine function. So the pattern then, you just have to break that in half to use this same technique. And that means instead of going in increments of pi over 2, I go in increments of pi over 4. And if you look at a tangent function here, and I can go to the simulation because it's a bit different. Remember, tangent actually represents the ratio of y over x. So it starts at 0 because y is 0 and x is 1. And then here, they're both equal, or roughly equal. It's hard to get this exact, but the tangent of 45 degrees, or pi over 4 radians, is 1. And then here, because the x value is approaching 0, it gets really big. And then, of course, right at 90, it's undefined because you can't divide by 0. And then over here, the x value is negative, so the tangent is negative because the y is still positive. And so that means here at 3 pi over 4, or abouts, it's -1, and then here it's 0 again. And then the pattern repeats down here because they're both negative. So y is negative and x is negative, so it cancels out, and that's why the pattern just completely repeats itself every pi radians. So if I'm filling this out, whoops, I would start at 0 for this one, which again, tangent here is 0. That's where I start. And then if I go in increments of pi over 4, here it's 1. And then here it's undefined, so I'll just write does not exist. And then at 3 pi over 4, it's -1. And then here it's back to 0. And then the exact same pattern repeats itself, right? It would be 1 here and does not exist here, and then it would be negative in quadrant 4. So using that, if I do have a tangent, and I won't do all the examples, I'll just try to get this one with a tangent. So this is the same technique. I'm going to take whatever the value is here, and this is where I'm going to start. So I'm going to start at pi, and tangent of pi here was 0. And then I'm going to go in the negative direction. So at 3 pi over 4, it was -1, and then here does not exist. And then here it was +1, and then 0, and on it goes. And so because it's just going to start with the -1 instead of the +1, this is just negative tan of theta.